Hello everyone, welcome to this presentation. My name is Antoine Defourné and today we'll present a joint work with Petar Vukmirovic about bringing higher order automations to TLAPS. So let's start with some context. I want to make clear that I will not talk about TLC and models in this talk. I will only be concerned with TLAPS and proofs, and also I will ignore temporal problems because they are not so much used in practice for TLAPS. The problem I'm concerned with is a class of theorems for TLAPS which are not handled very well currently by the backend solvers because they are more second order problems which cannot be handled by first order backends. So I want to extend TLAPS with a new higher order backend solver, and for this I chose superposition. So let me explain quickly how TLAPS works for those of you who never used TLAPS. So the tool is able to parse a module for theorems and proof scripts, and from these proofs generate a number of proof obligations which correspond to proof steps in the script. Each proof obligation is then sent to a backend solver, to all of the backend solvers of TLAPS after being encoded in the respective input languages. And whenever a solver answers that a proof obligation is valid, it is trusted by TLAPS and the proof obligation is considered valid. So there are several backends available: Isabelle, Xenon, a few SMT solvers, and PTL for the temporal reasoning part. So to illustrate my problem, let's start from a definition. So I want to define a sum operator in TLA+, and I want to do it by recursion. So in this expression there are two parameters. There is the natural number n and the series s. For n I can just represent it using a natural number of TLA+, but for s I have a choice. I can use a TLA+ function or an operator. So I chose an operator for this, for the sake of illustration, because that will make the sum operator parameterized by another operator, so it will be second order. Here is a definition. There is a difficulty with this definition because TLA+ doesn't allow to define recursive operators, only recursive functions. So this is why I have to do it in two steps like this. Now, another issue with this definition is that when a recursive function is defined like this, it's actually a choose expression behind the scenes. So sumrec must be read as some function f, such that f is a function on NAT that matches the recursive definition, if it exists. If such function doesn't exist, then the definition can't be used. So the user must prove by itself that such a function exists before the definition can be used for anything. Fortunately, the standard distribution of TLAPS provides a module to do just that. And if we follow a simple pattern of theorems, we can recover the basic facts and the basic properties of the sum quickly. So it works like this. First, I have to prove the theorem subdef conclusion, which I won't explain, but it states in some way that the function f that matches the recursive definition does exist. And you see here that the theorem has to be parameterized by an operator s. This is the assume new s part. I'm skipping the proof, but just know that this is solved by TLAPS without problem. Now, the theorem I'm interested in is SumDef. SumDef states that the sum operator for argument n and s is defined by the recursive definition that I intended. So this is a statement that I would like to use instead of the actual definition of the operator whenever I need to use the sum definition. In principle, SumDef is just a reformulation of SumDef conclusion. So its proof is just one line here, and it works by invoking SumDef conclusion as a lemma and expands some definition. Now, unfortunately, this proof fails. TLAPS is not able to prove this one. To understand why, let's look at SumDef conclusion. So I already pointed out that SumDef conclusion is parameterized by an operator S. In logical terms, that means SumDef conclusion is a statement that is quantified over operators, over an operator S. And for SumDef, this quantified lemma has to be instantiated with an operator S. So we can see that it's not first order instantiation here, it's second order instantiation. And well, most of the backend solvers of TLAPS are only able to handle first order instantiation because they are first order logic. And Isabelle is the only backend that can do that. So that makes the proof very fragile. And because Isabelle is not able to prove this one, TLAPS cannot do anything more, and the proof fails. Okay, so we can state in general what problems are not going to be handled well by TLAPS. Every time a lemma that is parameterized by an operator is invoked in a proof, and that lemma has to be used, so to be instantiated with an operator, this is a second order problem. So we can't use the backend, the first order backends at all for those. As a special case, we can see constructs, primitive constructs like set comprehension, for example, but also choose expression functions and so on, has second order constructs with not axioms but axiom schemas parameterized by an operator, predicate P in that case, and those axiom schema needs to be instantiated for the encoding. So of course these are common constructs, so for the first order encodings we have to handle them in some way, and currently this is done by eliminating those problematic constructs. So here you can see one example just to give the idea. So if I want to eliminate the set comprehension for this predicate, I can start by rewriting it as a second order application, so with one argument being the base set but the other one being a predicate, the predicate P. And then what I need to do is to replace this application by another application with a new declared operator which is specialized for this predicate. And I also need to provide the axiom, the instance of the axiom schema for set comprehension for that predicate, and that's it. There are complications when some local variables are involved. See in that example, we need to make some arrangement, provide C as a parameter, but this is something that we are able to do in cases such as this one, because we know the axiom schema behind the construct. Now, if I don't want to do this rather technical elimination procedure, I can just encode the problem into higher order logic and send the higher order problem to a solver which is able to handle higher order logic. We chose superposition to make this experiment. Superposition is a first order superposition solver which was extended to higher order logic recently. To give you more context, this is part of a project called Matryoshka and supervised by Jasmin Blanchette, which is about extending solver from first order to higher order logic in a way that preserves their good properties. And superposition just won the CASC competition last year in the THF division. THF is a component of the TPTP standard language for problems, and it covers higher order logic. So we did the implementation. We implemented it at the module, so an export from TLAPS to THF. The important aspect of this is that we don't need to eliminate the higher order features anymore, so we can translate the problem more directly than before. And using this, using superposition, we were able to solve the sum example rather easily. Now there are still some work to do. So our priority right now is to make this new superposition backend as efficient as the first order backends of TLAPS. So the first order of encodings are well optimized by now, especially the SMT encoding. So we could test this one some example, but to evaluate it on a larger base of examples, we still have work to do. The next step will be to mix higher order reasoning with theories, especially arithmetic. Here the problem is that superposition is extended to higher order logic, but this extension is not compatible with special reasoning like arithmetic, so we cannot use the backend for obligations that mix higher order with arithmetic, for example. So we need to find a solution for that yet. And then the next step, maybe more long-term objective, would be to attempt an encoding based on the sets as predicates principle. The idea for this encoding is that we can encode sets as predicates which are satisfied by the elements of that set, and those elements only. And set membership is encoded as functional application in higher order logic, very simply. So here you can find some examples, very easy to understand how this works. And the interest of that encoding will be that we don't need to declare many new operators and axioms in the resulting file, because each set can just be represented by a lambda term, and that is all. Okay, so this is the end of the talk. Thank you for your attention. If you have any question, I'm ready to answer them now.